Okay guys, today I will finally explain how the Type 3 compensator is designed for a buck converter. But before jumping in LTSPICE, I should do before some theory. So let's start from the fact that DC-DC converters have some problems connected with the poles and zeros. So if you study the transfer function of a buck converter, you will discover that basically you know that the buck converter has the high side switching, the diode here, and the LC group at the output with L and C here, plus the ESR. So this the LC is causing a double pole and the ESR is causing a zero. So you will not be surprised if the transfer function of a buck converter should be like this: minus 40 and minus 20 dB, where this is the double pole caused by the LC and this zero is caused by the ESR of the output capacitor. So it is quite reasonable to say, I will skip the demonstration because it is really longer than you think. It is reasonable to say that it has two fixed poles and one zero at the owing to the ESR. So you should expect, as I said before, something like this. As you can see, here there is the pole of the double pole of the output capacitor, LC, as you can see the square root of LC, and here instead there is the zero of the ESR. In order to create any compensator in a DC-DC converter, you should put always a infinite gain, so like an integrator, ideally, because you want the DC-DC you want the DC gain to be basically infinite. If you sum these two transfer functions, so the integrator plus this, what you obtain is called the Type 3 compensator. So the missing transfer function that can really give you the integral gain, the infinite integral gain. And basically this is the transfer function of the Type 3 compensator. So let's analyze this. Let me prolong this. So basically, if you just do this summation here, you won't obtain these two zeros. These two zeros are split to make another gain, A1 lower than A2, to make an optimization in the low frequencies. And to design this in a compact way with an op-amp, what you should do is to put a combination of capacitor and resistor in order to have a programmable gain in different frequencies. So basically, how does the compensator Type 3 works? The circuit, so the main circuit is done like this. It has two impedances, Z1 and Z2, and by putting all these capacitors, these capacitors basically act like a switch, like switches in the frequency domain. What I'm saying is that basically this capacitor, this C1, C2, and C3 will be opened at different moments and will be shorted at different moments. So you do remember that when you have a capacitor, the capacitor has a behavior like 1 over J omega C. So if omega tends to 0, you see that the capacitor behaves like an open for a DC. So for a DC current, the capacitor behaves like an open. But if you put omega to infinite or a very, very high omega, and C is also small, what you obtain is that the capacitor is basically a short. And this notion will be extremely useful for the studying of the type-free compensator. So this capacitor C1, C2, C3 can be capacitors, short circuits, or open circuits. So if you make an example, when you are in the range of A2, I make just an example, when you are in the frequency range of A2, the capacitor C3 is a short, and so you have R3, R1, and R2. Also G2 will be a short, and C1 will be an open. And so basically, as you can see, the circuit behaves like a PI, like an integrator, and the gain A2 will be equal to minus R2 over R3 in parallel with R1. And basically this is all the formula that you can find in any application note or in any power electronics course, because as you can see, all these poles, all these formula are calculated with the fact that the capacitor can act like a short, open, or capacitor itself. And as you can see, the gain A2 is exactly as I told you. You can do the same as the gain A1, because basically the capacitor here, C3, will practically short the R3, sorry, it will practically be an open, and so you will have just R3 will be will not be considered since C3 is an open, and you see that the gain A1 is R2 over R1. And it has to be lower since A2 has the parallel under the denominator. So, in order to design the type-free compensator, you need a precise algorithm. You have to start from this. You know that from the design of a buck converter, you will have the value of L, you will have the value of C, and you will have the switching frequency. You will fit that everything on this algorithm in order to study all the components needed for the compensator. Let me give just a bit of a hint because it is quite long. So you start from the step 1. You know that it has double pole on 2 pi LC0, and you derive the first 0 F2 here. So from this equation, you derive FZ2, which is basically this. Now, once you have the FZ2, you can say that this is half of the second 0, and as you can see, from Z2 you derive FZ1. And you go on in following this step. You can find also different steps in other application note. As you can see, you choose the crossover frequency FC based on the switching frequency over basically 10. I have made luckily for you, I have already made this. As you can see, you put the inductor, you put the capacitor, and everything will come out from your Excel. There are also, I think that there are also some tool online. You can also use that. So there are quite standard compensator. So now that we have done this brief of theory, let's jump on LTSPICE. So before simulating the type-free compensator, let's start from a buck converter. As you know, I will do it very fast because if you already watched my video, you can find also tons of video in how to design a buck converter. Just put 2 MOSFET here. Just put the first of the list. $56 micro, 20 volts, and output capacitor of 500 micro. The load equal to 1, and I think that there is no reason to test the open loop buck because they are just basically 2 switches. And before putting the type-free compensator, we should at least test the type-free compensator in another paper. So let's open another draft and let's put the type-free compensator that I designed. So you start from here. This will be your impedance Z1, and this will be your impedance Z2. Let's put the op-amp, universal op-amp 2. There will be the reference voltage, but since we are just testing the transfer function, we don't care. Now we put the values that I designed. Let me put in order with according to the so yeah, this is R1, this is R2, and this is R3. Okay, this is now correct. And R3 and R3 goes with C3. So the first capacitor is C1 here, and C2 with R2, and C3 with R3. And you put in the minus. Oh, by the way, you can even use just universal op-amp 2. I think that since this is just a transfer function, this is the output voltage, this is the input voltage, and we are going to just put the AC amplitude equal to 1 to in. Don't forget to write .lib opamp.sub, otherwise it won't work. Now let's put the values. 10 nano, 4.7 kilo, 8.2 kilo, 22 kilo, 100 pico, and 50 nano. Let's run the simulation in AC analysis. Decade, 1 points for decade, start frequency 1, stop frequency 1 MHz. Meg. So yeah, that's basically, okay, this is correct, and that's basically the type-free compensator. As you can see, there is the gain, so you can recognize the two gains here. The first gain, the two zeros, so as you can see, I put the F0, F2 at 90 and 951. Let's see if it is true. At yes, as you can see here, there is the 0. Let me draw cursor position, and the other 0 to the other half. Yeah, more or less it is like I designed. Of course, in real transfer function, don't expect to have something so linear like this. So don't as you can see, it is very, very curvy. So don't expect to find the poles so easily. So this is 60 dBs, and here should be 10 dBs. Sorry, 11 dBs. Okay, now that we saw that the transfer function is exactly as we planned, as you can see here at 100 kHz is already cutting off everything from 1 kHz forward. So now let's put this compensator. Let's put the compensator in the circuit. Oh, come on. Okay, we can close this. Just have this. Okay, so let's connect the output here to the impedance Z1, and let's connect the plus with the reference voltage. Let's make 5 volts. Something is wrong. Okay, now it is correct. It is suggested to put the universal op-amp because this time you will need the hysteresis. And so remember to put the reference on the plus side. This is extremely important. The reference on the plus side and the compensator on the negative side. Then let's decide the power supplies. Let's call it V plus and let's call it V minus. These two are a reference to ground because they are just power supplies. Let's put minus 50 volts and plus 50 volts. So after the output, you will need, as you know, you will need. Let me just rephrase a bit. After the compensator, you will need to compare the compensator net with a triangular waveform, and this will go into the duty cycle of your MOSFET. So now let's put the triangular, the sawtooth. I need just the switching frequency Fs equal to 100 kHz, dot param Fs equal to 100 kHz, and dot param nothing. Just the switching frequency. So now let me put the pulse 0, 3 volts, delay not important, rise 1 over 2 times Fs, the same from the fall, and the same NT on just 1 nano, and the period 1 over Fs. And you should be. And this is an error because I didn't put the... My teacher said that I make always the same mistakes, and it is true. So let's call it VSAW. And the sawtooth. Now, these two... No. No. And these two goes inside the op-amp. Remember to put the sawtooth, the comparator on the plus and the sawtooth on the minus. So now let's put V plus here and V plus here, V minus here, and V minus here. Now let's close the loop with the PWM. By the way, here I forgot the input capacitance, but in LTSPICE is not so important because it is just a parallel with these two. So let me just close the loop with the voltage E1 and let's call it let's toggle this, and I will show why I don't like the solution with the diode. Okay. So now let's set the reference voltage and let's set the load to 1. Now we can run the simulation from 10 milliseconds and let's see what happens. Okay, something is clearly, okay, something is wrong and we have to understand. V plus, V minus. Let me... So yeah, it is very strange. Let me skip the initial. Maybe I just forgot. Probably I just forgot something. Okay. I don't know what happened. Okay, so now let's run. Now let's see what is happening. You check the reference voltage, which is 5 volts, and you check the output voltage, and you say, "Wow, it is working." The answer is yes, but you have also always to check what is going on in the duty cycle, because this behavior is not so beautiful. From what I'm seeing, is just he's starting to turn off the buck converter, which is not good. And to verify this, my theory, just see always check the VGS voltage of the high side. And as you can see, the high side MOSFET has minus 15 volts here, so meaning that the buck converter is basically off. So it is not switching here, and as you can see, it is not even behaving well. This is very, very, very wrong. Okay, this is not so. The transient is not so beautiful, and also the steady state VGS, it is not quite remarkable. So what I would suggest here instead is to use instead the double configuration, because the synchronous configuration. So you just put another MOSFET, you just put the same MOSFET here, and you put the same PWM, but with -1. Now let's run the simulation again. Oh, now it makes more sense. So as you can see, it is better the synchronous configuration, not only because it dissipates less, but also because it is working more properly. So now, as you can see, it is true that the duty cycle of this is negative, but the duty cycle of this will be high, and so you are forcing the low side to conduct current, and the buck converter is never off. And so you see now the proper oscillation of the transient of the buck converter. Basically, this will change with the load, because you are switching from the CCM to DCM, and if you put a very, very high load, this will be basically a disaster, as you can see, because this is a DCM condition, and the buck converter is not designed for DCM condition. So let me just put 1 ohm load. Let me just play a little bit with the reference. As you can see, it follows quite well the reference, and if I put 15 volts as a reference voltage, you see that it will follow smoothly the reference, as a buck converter actually should. we can increase the switching frequency in order to reduce the ripple, since silicon MOSFET and low power and this low power MOSFET can go even at higher frequencies, even like 50 kHz. It is true that you should redesign. I don't know if it is gonna work, because you should even redesign. As you can see, it is not gonna work, because you should redesign the compensator to make it work at this frequency. Because as you can see here, I choose the switching frequency of 100 kHz. If I choose the other switching frequency, 200 kHz, you see that some values are gonna change. So let me put again 100 kHz, and I think that we can stop the video for today. As you can see, I promised you to make the oh, maybe if we just put I'm just trying something. Don't mind me, because I'm just trying something. Did it improve? No, not quite. It has worsened a bit. No, this isn't. No. This, by the way, was just my experiment. No, this is just an experiment. Don't mind me. So, thank you for this video. Thank you for this video, and see you on the next one. Bye bye.